Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with the Moon's formation, a reflection on the giant impact theory. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet. The universe is vast, and we are ready to explore. This celestial body has transcended mere presence, becoming a vital component of Earth's geological and biological narrative. Over 4 billion years ago, it emerged from the remnants of a colossal impact between a Mars-sized body and the early Earth. This event not only shaped the Moon, but also influenced Earth's rotation and axial tilt, contributing to the stability of its climate. The Moon's gravitational pull plays a pivotal role in the rhythmic rise and fall of ocean tides, a phenomenon that has profoundly influenced marine ecosystems and, by extension, terrestrial life. These interactions have fostered conditions conducive to the development of complex organisms over millennia. In addition to its physical influence, the Moon has served as a cultural and scientific touchstone throughout human history. Early civilizations revered it, attributing various mythologies and rituals to its phases. The advent of telescopic observation expanded its significance, revealing craters, maria, and regolith, which have become focal points for lunar exploration. Scientific endeavors, including robotic missions and manned landings, have unveiled its surface composition and geological history. This exploration has provided insights into not only the Moon itself, but also the broader solar system, establishing it as an essential key to understanding the origins of planetary bodies. Thus, its significance extends beyond Earth's immediate orbit, linking humanity to the cosmos. Early theories of lunar formation often reflected the scientific understanding of their time. Ancient civilizations proposed various mythological explanations, attributing the Moon's existence to deities or celestial beings. The Greeks, for instance, envisioned it as a celestial body created by divine forces, while others reflected on its relationship with Earth, emphasizing its role as a companion in the night sky. With the dawn of the Enlightenment, a shift occurred, paving the way for more empirical approaches. Philosophers like René Descartes speculated that the Moon formed from debris cast off during the creation of Earth. This idea gained traction, suggesting a violent genesis linked to the primordial chaos of the cosmos. In the 19th century, advances in observational astronomy led to further hypotheses. Theories emerged positing that the Moon was a captured body, a rogue planet ensnared by Earth's gravity. This notion reflected the growing understanding of gravitational interactions in the universe. By the 20th century, the advent of space exploration provided critical data. Sample collections from lunar missions revealed the Moon's geological composition, prompting a re-evaluation of previous theories. The giant impact hypothesis emerged as a leading explanation, suggesting that a Mars-sized body collided with the young Earth, resulting in the Moon's formation from the ejected debris. This theory synthesized earlier ideas, grounded in observable evidence. The formation of the solar system plays a critical role in understanding the Moon's origins. Within this primordial context, the protoplanetary disk, composed of gas, dust, and other materials, coalesced to give rise to various celestial bodies, including planets and moons. It is within this swirling mass that the Moon's eventual formation can be traced back to an era characterized by violent collisions and dynamic interactions. Interactions among early planetary bodies led to significant impacts, one of which is believed to have formed the Moon. The remnants of these collisions provide important clues regarding the early solar system environment. They reveal the conditions under which the Moon formed, as well as the materials that contributed to its composition. Isotopic analyses of lunar samples indicate a striking similarity to Earth, suggesting a shared origin. The gravitational influences within the nascent solar system contributed to the Moon's stable orbit. This relationship has implications not only for understanding lunar geology, but also for the evolution of terrestrial planets. The gravitational pull between Earth and its satellite has shaped climatic and geological processes, influencing the development of life on Earth. Researching these connections offers insight into the broader dynamics of planetary formation, illustrating how the Moon serves as a time capsule of the solar system's early history. Each discovery deepens knowledge of not only the Moon but also the intricate web of interactions that govern celestial evolution. The giant impact hypothesis proposes that a Mars-sized body, often referred to as Theia, collided with the early Earth approximately 4.5 billion years ago. This colossal event is believed to have been instrumental in shaping the Moon's formation. The energy released during the impact was immense, leading to a significant portion of Earth's outer layers and Theia being ejected into space. These ejected materials coalesced over time, driven by gravitational forces. For this scenario, the Moon is thought to share a similar isotopic composition with Earth, indicating a common origin. The dynamic nature of this early solar system environment, characterized by a multitude of colliding bodies, contributed to the evolution of planetary bodies and their satellites. Understanding this foundational event not only elucidates the origins of the Moon, but also provides insights into the conditions that prevailed during the formation of terrestrial planets. This model continues to be refined through ongoing research, particularly with advancements in observational technologies and analytical techniques. The conditions on the early Earth were markedly different from those observed today. A molten surface characterized by extreme temperatures existed, resulting from intense volcanic activity and frequent collisional events with planetesimals. This environment was hostile, with an atmosphere laden with gases such as carbon dioxide, nitrogen, and water vapor, yet devoid of free oxygen. The planet underwent significant differentiation, where heavier elements sank toward the core, while lighter materials formed the crust and mantle. These processes contributed to a dynamic geological landscape marked by the emergence of proto-continents and vast oceans of molten rock. Water vapor released from volcanic eruptions contributed to the gradual cooling of the surface, eventually forming bodies of liquid water as temperatures decreased. During this time, the solar system was still in its formative stages. The remnants of the protoplanetary disk were populated with debris and small celestial bodies, which frequently bombarded the Earth. This chaotic environment not only shaped the planet's surface, but also set the stage for the eventual cataclysmic event that would lead to the Moon's formation. The collision with a Mars-sized body, now referred to as Theia, would alter the trajectory of Earth's history. This impact would eject material into orbit, eventually coalescing to form the lunar body, a process pivotal to understanding the evolution of both Earth and its satellite. Theia, a hypothetical planet seismal, is thought to have played a crucial role in the formation of the Moon. This celestial body, roughly the size of Mars, is theorized to have existed in the early solar system as it collided with the young Earth. The immense energy released would have vaporized significant portions of both bodies. This event would create a cloud of debris, a mixture of silicate rock and metal, which began to orbit the Earth. The remnants of Theia contributed vital material to the lunar formation process. The energy from the impact heated this debris, allowing it to melt and eventually coalesce into a singular body. This region, now known as the Moon, bears the scars of its violent beginnings, evident in the craters that pockmark its surface. These features serve as a record of the Moon's tumultuous history and the impacts it has endured over millions of years. The gravitational influence of Earth helps stabilize the Moon's orbit, allowing it to cool and solidify. The composition of lunar basalt and highland rocks suggests a shared ancestry with both Earth and Theia, providing insights into the processes that shaped our planetary neighborhood. Understanding Theia's role enhances comprehension of planetary formation and the dynamics that govern celestial collisions in the early solar system. The formation of the solar system occurred approximately 4.6 billion years ago, a time marked by a swirling disk of gas and dust. This region, filled with volatile materials, facilitated the birth of planetary bodies through a process known as accretion. In this chaotic environment, protoplanets began to emerge, colliding and coalescing over millions of years. The inner solar system was dominated by rocky planets, each vying for dominance in a rapidly evolving landscape. The gravitational pull of larger bodies intensified, leading to a series of significant impacts that shaped their development. These collisions became increasingly violent as protoplanets grew to substantial sizes, leading to a tumultuous series of events. Around 4.5 billion years ago, a catastrophic encounter occurred. Theia, a Mars-sized body, collided with the early Earth in a collision of unprecedented magnitude. This impact was not merely a chance event, but rather a consequence of the dynamic and volatile environment prevalent at that time. The aftermath of this collision resulted in the ejection of debris into orbit around the Earth, which over time coalesced to form the Moon. This formation process provided critical insight into the development of both Earth and its satellite, marking a pivotal point in the history of the solar system. The Moon's subsequent evolution reflects the complex interplay between celestial bodies during their formative years. The accumulation of planetesimals serves as a crucial component in shaping the Earth-Moon system. These small Seek solid objects coalesced in the primordial solar nebula, gradually forming larger bodies through gravitational attraction. Their collision and merging contributed significantly to the mass of the early Earth, fostering an environment ripe for further development. This region of the solar system was characterized by a rich diversity of materials, including metallic and rocky fragments, which influenced both the terrestrial planets and their satellites. As planetesimals collided, they released energy, resulting in heat generation that promoted the melting of certain elements. This melting allowed for the differentiation of materials, leading to the formation of a layered structure within the emerging Earth. The remnants of these collisions, along with the materials ejected during the giant impact, played a vital role in forming the Moon. Over time, debris from the impact coalesced, driven by gravity, eventually leading to a single, stable satellite. The Moon's surface, marked by ancient crustal features and basins, tells the story of its violent beginnings and subsequent evolution. As the Earth and Moon continued to interact gravitationally, their relationship became more complex. This dynamic, characterized by tidal forces and orbital changes, shaped not only the current configuration of the Earth-Moon system, but also its long-term stability. The dynamics of collisional interactions in the young solar system established a chaotic environment filled with debris and potential collisions Within this tumultuous expanse, celestial bodies, including protoplanets and smaller asteroids, frequently collided. These interactions were not random. They followed specific gravitational influences that directed their paths. The energy released during these collisions could lead to significant alterations in the structure and composition of the impacted bodies. Smaller fragments, when colliding with larger bodies, could create craters and eject material into space. The products of such events contributed to the growing mass of planets, including Earth. This process of accretion was crucial as it allowed for the gradual accumulation of matter, leading to a more stable planetary structure over time. The aftermath of these impacts would influence not only the physical landscape of what would become the Earth and Moon, but also their atmospheres and potential for habitability. Interactions between colliding bodies often resulted in the production of debris disks, remnants of collisions that could coalesce into new moons or ring systems. The gravitational interplay within these disks allowed for the formation of satellites around larger bodies, enhancing the complexity of their orbits. Such processes laid the groundwork for the diverse range of celestial systems observed today, sculpting the architecture of the solar system into its current form. Impact events significantly influenced the development of planetary bodies, leading to the restructuring of their surfaces and atmospheres. In the early solar system, collisions were frequent and varied in scale, occurring on a time scale measured in millions of years. These interactions shaped not only terrestrial planets, but also moons and smaller bodies within the asteroid belt. The magnitude of these impacts ranged from smaller asteroids, which caused localized craters, to massive collisions that resulted in the formation of new celestial bodies. Each encounter contributed to the ongoing process of planetary evolution, as debris from collisions often coalesced, forming larger aggregates. This environment fostered the eventual emergence of stable planetary orbits. Notably, the Moon's formation is attributed to a significant impact event where a Mars-sized body collided with the early Earth. This collision ejected vast amounts of material into orbit, which later coalesced to form the Moon. The dynamics of such impacts highlight the chaotic and violent nature of early planetary formation. In this context, the frequency of impacts diminished over time as planetary bodies grew larger, their gravitational influence becoming more pronounced. The remnants of these ancient events are still visible today, preserved in craters that dot planetary surfaces, offering insights into the history of our solar system's evolution. Each crater tells a story of the violent past, encapsulating moments that shaped the very nature of celestial bodies. The energy released during a giant impact is staggering. Measured in quintillions of joules, this immense force can alter trajectories and reshape planets. The physics behind such events reveals a complex interplay of kinetic energy, gravitational forces, and thermal dynamics. Upon collision, the rapid deceleration of celestial bodies generates shock waves that propagate through solid and molten material. The resulting heat can cause temperatures to soar, resulting in the vaporization of surface materials and the formation of a transient atmosphere. This region surrounding the impact site becomes a crucible for transformation. As debris is ejected into space, gravitational forces begin to pull fragments together, allowing for the accumulation of matter that can lead to planetary formation. In the case of the Moon, the collision between the early Earth and a Mars-sized body created a significant amount of debris that eventually coalesced into the lunar surface. The aftermath of such impacts influences geological evolution. Crater formation can reveal the history of impacts over eons. illustrating how these events contribute to planetary development. Erosion, volcanic activity, and tectonic processes further modify the landscape, obscuring some evidence while preserving others. The intricate relationship between energy release and subsequent geological changes is an essential aspect of understanding planetary evolution, particularly in the context of Earth's natural satellite. Simulations of Thea's collision provide invaluable insights into the dynamics of this monumental event. These computational models recreate the conditions of the early solar system, allowing scientists to explore various scenarios of the impact by adjusting parameters such as the size, velocity, and angle of Thea's approach. Researchers can observe the resulting interactions between the two bodies. The simulations reveal that a high-velocity impact would have led to significant fragmentation of both Thea and the early Earth. This debris, propelled into orbit, would eventually coalesce to form the Moon. Variations in the angle of impact illustrate how a more oblique collision could produce different outcomes, influencing the subsequent composition of the lunar surface. These models also allow for the examination of energy transfer during the collision. The immense kinetic energy released would have melted substantial portions of both planetary bodies, contributing to a magma ocean on the early Earth. Such simulations indicate that the temperatures and pressures involved were sufficient to cause the differentiation of materials, an essential process in the formation of the terrestrial planets. By refining these computational techniques, scientists can enhance their understanding of early planetary dynamics, shedding light on the origins of the Moon and its role in Earth's geological history. Insights from these models continue to shape our comprehension of celestial mechanics and planetary formation. Angular momentum plays a crucial role in the dynamics of the Earth-Moon system, influencing both the formation and the subsequent evolution of this celestial pairing. The collision that led to the Moon's creation imparted significant angular momentum, dictating the initial rotational speed of the nascent Earth. This momentum not only contributed to the Earth's current day length, but also established the Moon's orbit, a delicate balance sustained through gravitational interactions over billions of years. The conservation of angular momentum explains the gradual transfer of rotational energy between these bodies. As the Moon orbits, it exerts tidal forces on Earth, resulting in energy dissipation. That within this framework, the dynamics of the Earth-Moon system provide insight into the broader mechanics of planetary systems. The angular momentum shared between Earth and its satellite fosters a unique environment, influencing atmospheric patterns, oceanic tides, and even biological rhythms. This interplay showcases the profound impact that angular momentum has on shaping not just the physical characteristics of celestial bodies, but also the intricate processes that govern life on Earth. The aftermath of the impact led to the creation of a vast lunar disk, composed of debris ejected into orbit around Earth. This expansive cloud of material, primarily consisting of silicate minerals and metal, began to coalesce under the influence of gravity. Over the course of several thousand years, the particles gradually merged, forming a proto-moon that reflected the chaotic conditions following the collision. Temperature fluctuations in this region were extreme, with the newly formed disk exhibiting a molten state that would later solidify as it cooled. The distribution of material was uneven, influencing the Moon's eventual geological diversity. Regions rich in iron settled towards the core, while lighter silicate minerals floated towards the surface, creating a layered structure. Volatile compounds were released during this period, contributing to the development of an early atmosphere around the Moon. This tenuous envelope however, was short-lived, as the lack of sufficient gravitational pull could not retain these gases. As the molten surface solidified, it formed the crust, characterized by the dark basaltic plains known as maria. Impact craters began to pepper the surface as smaller debris continued to bombard the young moon. This formation process not only shaped the moon itself, but also influenced the Earth-Moon dynamic, affecting tides and stabilizing Earth's axial tilt over time. Understanding the composition of the moon reveals profound insights into its differentiation. This process began with the intense heat generated by the giant impact, causing materials to melt and allowing denser substances to settle toward the center. Elements such as iron and titanium became concentrated in the moon's core, while lighter materials, including silicates, formed the outer crust. The crust exhibits a diverse mineralogy, primarily composed of plagioclase, pyroxene, and olivine, indicative of a history shaped by volcanic activity and subsequent cooling. This region's surface features, including maria and highlands, provide a geological record of past events. The basaltic plains, formed from ancient lava flows, contrasts sharply with the more rugged highlands, reflecting a complex interplay of volcanic and impact processes. Analysis of lunar samples collected during the Apollo missions has further revealed the moon's isotopic composition closely resembles that of Earth. This similarity strengthens the giant impact hypothesis, suggesting a shared origin among terrestrial planets. Geophysical studies indicate the moon's interior may still harbor remnants of its formative processes. Seismic data, gathered from instruments left on the lunar surface, reveal insights into its layered structure, offering clues about its thermal history and potential for past geological activity. Each observation adds another layer to the understanding of this celestial body, illuminating its role in the broader context of planetary formation. The hybrid composition of the moon reveals the intricate interplay between Earth and Theia, a Mars-sized body that collided with the early Earth. This collision resulted in the ejection of a significant amount of material into orbit, giving rise to the moon. Isotopic analyses demonstrate remarkable similarities between Earth's rock samples and those from lunar missions. Such findings indicate a shared origin, pointing to a mixing of materials during the cataclysmic event. Geochemical studies further unveil the nuanced nature of this composition. The presence of specific elements and isotopes in lunar samples aligns closely with those found on Earth, suggesting a complex interaction between the two bodies. This region of the moon's surface, characterized by anorthositic highlands and basaltic maria, provides a glimpse into this hybridization process. These formations, shaped by volcanic activity and subsequent impacts, bear witness to the tumultuous history of the moon's evolution. Petrological evidence supports the notion of remelting and recrystallization, processes that facilitated the blending of Thean and terrestrial materials. The ongoing analysis of lunar regolith reveals the dynamic environmental conditions that played a role in shaping the moon's surface. Insights gained from these studies continue to refine current models of planetary formation, illustrating the moon as a product of cosmic cooperation and collision. Isotopic analysis reveals intriguing parallels and distinctions between the moon and Earth, deepening the understanding of their shared origin. Both celestial bodies exhibit similar isotopic signatures in oxygen, indicating a common source in the primordial solar nebula. This resemblance suggests that they formed from similar materials, contributing to the theory of a singular event catalyzing their creation. Contrastingly, discrepancies emerge when examining certain isotopes particularly in the case of titanium and tungsten. These variances imply that the Moon underwent a unique set of processes post-impact, leading to its distinct compositional traits. The lower levels of volatile elements on the lunar surface indicate a history of higher temperatures, potentially due to the energy released during its violent formation. In this context, the isotopic differences reflect not only the dynamics of impact, but also the subsequent evolutionary paths of the two bodies. Earth's atmosphere and hydrosphere enabled the retention of volatile compounds, while the Moon, with its lack of substantial atmosphere, lost much of its primordial inventory to space. This intricate interplay of similarities and differences enriches the narrative of planetary formation and evolution. Understanding these isotopic relationships fosters deeper insights into the conditions present in the early solar system and offers a clearer picture of how terrestrial worlds develop over time. The presence of volatiles in lunar samples provides critical information regarding the Moon's formation. These elements, which include water, hydrogen, and carbon compounds, are often considered key indicators of the conditions under which celestial bodies form. Analyzing the distribution and abundance of volatiles reveals insights into the processes that shaped the early lunar environment. Volatile elements are surprisingly scarce on the Moon's surface, leading to hypotheses about its formation. This scarcity suggests that the Moon underwent significant heating and differentiation following its creation. The intense energy from the giant impact likely caused the vaporization of many volatile components, leaving behind a dry, barren landscape. The stark contrast between Earth and its satellite highlights the different evolutionary paths taken by these bodies. Recent studies indicate that some volatiles may have been retained in the lunar interior, potentially preserved within mineral structures. These trapped elements could offer a glimpse into the primordial materials that contributed to the Moon's formation. Ongoing research aims to further explore these hidden reservoirs, potentially illuminating the conditions of the early solar system. Understanding the role of volatiles not only refines existing models of lunar formation, but also aids in comprehending the broader context of planetary evolution. Insights gained from the Moon may illuminate the processes that formed its surface features. Geological evidence reveals a landscape shaped by a complex interplay of impacts, volcanic activity, and space weathering. The presence of vast basalt plains, known as maria, indicates ancient volcanic eruptions that occurred after the colossal impact believed to have created the Moon. These smooth expanses, darker in hue compared to the surrounding highlands, serve as a testament to the planet's fiery past. Crater formations scatter across the surface, each representing a historical record of collisions with asteroids and comets over billions of years. Their varied sizes and depths provide crucial data regarding the Moon's geological history. The density of these craters suggests a significant period of bombardment, a phase that shaped not only the Moon but also the early Earth. The myth suggests that they formed from similar materials, contributing to the theory of a singular event catalyzing their creation. Composed primarily of anorthosite, these regions reflect the Moon's ancient crust, formed during its initial cooling phase. Layers of regolith, created by the incessant micrometeorite impacts, blanket the surface, adding another dimension to the Moon's geological timeline. Studies of these features not only clarify the Moon's origin, but also enhance understanding of planetary formation processes across the solar system. Evidence of the Moon's turbulent early history is prominently displayed through its cratering. Each impact crater serves as a record, capturing moments from a chaotic epoch. when the young moon was subjected to relentless bombardment. The diversity in size and morphology of these craters speaks to the various forces at play during that time. Larger craters, often surrounded by intricate ejector blankets, reflect the energy released from massive collisions, while smaller craters reveal the ongoing activity of micrometeorites that continue to shape this celestial body. The absence of an atmosphere has allowed these features to remain largely unchanged, preserving a snapshot of the moon's formative years. Over billions of years, the surface has remained exposed, enabling scientists to study the stratigraphy of these impacts. Each layer of regolith formed from the shattered rock provides insight into the frequency and scale of impacts, allowing researchers to construct a timeline of significant events in the moon's history. Variations in crater density across the surface indicate regions that have endured more significant impacts compared to others. This uneven distribution offers clues about the dynamic processes that influenced the moon's evolution. The study of cratering not only elucidates the moon's past, but also contributes to a broader understanding of impact processes in planetary science. The moon's thermal evolution post-impact reveals a complex interplay of geological processes following the colossal collision that formed it. The surface experienced intense heating, leading to the melting of vast regions. This resulted in the differentiation of materials, with heavier elements sinking and lighter ones rising. The consequences of this primordial event can still be observed in the composition of lunar rocks, which exhibit a range of mineralogical variations. Cooling occurred over millions of years, allowing the formation of a solid crust. The initial magma ocean, a consequence of the heat generated by the impact, gradually crystallized, contributing to the moon's basaltic plains known as maria. These dark, basaltic regions are not merely aesthetic features, they are critical indicators of the moon's volcanic history, marking periods of extensive volcanic activity. Subsequent geological processes, including the effects of solar wind and micrometeorite impacts, contributed to the gradual weathering of the surface. Over time, regolith developed, forming a fine layer of dust and shattered rock. This regolith composition offers insights into the moon's thermal history and the ongoing processes that shape its landscape. The moon's relatively stable interior suggests that significant thermal evolution ceased long ago. Evidence of this is reflected in the lack of substantial tectonic activity, allowing its geological features to endure through eons. The surface of the moon reveals vast, dark plains known as lunar maria, formed primarily by ancient volcanic activity. These regions, characterized by their basaltic composition, were created during a period of intense volcanic outgassing and lava flow. Initially, the moon's crust was thinner in certain areas, leading to the formation of large basins due to impacts from celestial bodies. Subsequent volcanic eruptions filled these basins with molten rock, solidifying into the smooth, expansive surfaces observed today. The eruptions that contributed to the lunar maria were relatively gentle compared to those found on Earth. These volcanic activities released basaltic lava, which flowed easily across the surface, creating the extensive dark plains. Evidence of this process is visible in the various features of the maria, such as the absence of large craters and the presence of extensive lava tubes. Understanding the timeline of this volcanic activity sheds light on the thermal evolution of the moon. The cessation of volcanism indicates a gradual cooling of the interior, leading to the formation of the rigid crust. This cooling process has left the maria relatively unchanged, preserving a record of the moon's geological history. Elevated regions, or highlands, surrounding these maria contrasts sharply with their smoother surfaces, providing insight into the complex interplay of impacts and volcanic processes that shaped this celestial body. Tidal forces exert a profound influence on the Earth-Moon relationship, fundamentally affecting both bodies over geological time. The gravitational pull between them creates tidal bulges on Earth, which manifest as rising and falling sea levels. This interaction is not merely a surface phenomenon. It extends deep into the planet's structure, influencing tectonic activity and geological processes. The Moon's gravitational influence stabilizes Earth's axial tilt, contributing to a relatively stable climate over millennia. Gradual tidal locking has occurred as a result of these forces, causing the Moon to rotate on its axis in sync with its orbit around Earth. This synchronous rotation means that only one hemisphere is perpetually visible from Earth, while the far side remains concealed. The differing gravitational forces between the near side and far side lead to variations in crustal thickness, creating a distinct topographical contrast. Over time, the Earth's rotation has slowed due to the energy dissipated in tidal interactions, gradually increasing the distance between the two bodies. Currently, the Moon recedes at a rate of approximately 3.8 centimeters per year. This ongoing process provides critical insights into the evolution of planetary systems and the dynamics of celestial mechanics, illustrating the delicate balance that governs the relationship between Earth and its single natural satellite. The initial trajectories of the Moon's orbit were determined by the mechanics of the giant impact that birthed it. Following the collision, fragments of debris coalesced into a singular mass, which subsequently began its orbit around Earth. This initial trajectory was influenced by the angular momentum of both the Earth and the material that formed the Moon, resulting in a complex gravitational interplay. Over time, the Moon's orbit stabilized, evolving into a nearly circular path that now defines its relationship with Earth. Long-term stability is maintained through gravitational interactions, particularly the tidal forces exerted by Earth. These interactions not only keep the Moon in orbit but also gradually influence its rotation. The synchronous rotation of the Moon, where one side perpetually faces Earth, is a consequence of this tidal locking, a process that unfolded over millions of years. The Moon's position and movement impact various terrestrial phenomena, including ocean tides and the axial tilt of Earth. These factors contribute to climate regulation and the stability of seasons. The delicate gravitational balance continues to govern the orbital mechanics observed today, underscoring the significance of the Moon in understanding both the historical formation of the Earth-Moon system and the ongoing evolution of planetary dynamics within the solar system. The kinetic energy generated by the colossal impact that birthed the Moon was immense, with estimates suggesting that it may have been equivalent to the energy released by several million atomic bombs. This energy, a direct consequence of the colliding bodies, influenced the debris cloud formation that eventually coalesced into the Moon. The collision velocity, which was likely in the range of several kilometers per second, contributed significantly to the energy budget of this event. The new iterations indicate that the impactor, a Mars-sized body, often referred to as Theia, struck the early Earth at an angle conducive to the ejection of a substantial amount of material. This material, propelled into orbit around the Earth, gradually accreted, forming the Moon. The dynamics of this process involved intricate interactions between gravitational forces and the energy dissipated during the impact. Thermodynamic modeling reveals that the heat generated from the collision played a pivotal role in melting a significant portion of the ejected material. Consequently, this resulted in a differentiated Moon with a composition distinct from that of the Earth. Observations of lunar geology support these findings, showcasing a history marked by intense thermal activity and subsequent cooling, which shaped the moon's surface and internal structure over billions of years. The legacy of this impact continues to influence not only the moon's characteristics, but also the evolutionary narrative of terrestrial planets. Computer simulations have emerged as pivotal tools in substantiating the giant impact hypothesis. These advanced models replicate the conditions surrounding the early solar system, allowing scientists to recreate the dynamics of a colossal collision by manipulating variables such as impact angle, velocity, and the composition of the colliding bodies. These simulations provide insights into the potential outcomes of such a monumental event. The results from these simulations often reveal a remarkable consistency with the current geological and compositional data of the Moon. Variations in the parameters can yield different lunar outcomes, yet many configurations lead to a satellite resembling the Moon we observe today. This alignment between simulated results and empirical evidence supports the theory that a Mars-sized body, often referred to as Theia, collided with the early Earth, resulting in the debris that coalesced to form the Moon. Furthermore, advancements in computational power have enhanced the precision of these models. Three-dimensional simulations allow for a more nuanced understanding of the aftermath, including the distribution of material and the thermal effects of such an impact. This meticulous approach aids in deciphering the complex interactions that shaped the Moon's surface and geological history. As research progresses, these simulations will continue to refine our comprehension of the events that forged Earth's natural satellite. Examining alternative theories provides additional context to the Moon's origin. The fission theory suggests that a rapid rotation of the early Earth caused a portion of its material to break away, eventually forming the Moon. This concept relies on the premise that the planet once spun at an extraordinary velocity, leading to the ejection of mass that coalesced into a satellite. Though intriguing, this hypothesis faces challenges in explaining the current angular momentum of both Earth and its Moon. Capture theory proposes that the Moon originated from elsewhere in the solar system, entering Earth's orbit due to gravitational interactions. This scenario posits that the Moon, perhaps a wandering body, was drawn in by Earth's gravity, a process requiring specific conditions for successful capture. While this theory accounts for certain compositional similarities between Earth and the Moon, it struggles to clarify how such a significant celestial body could be captured without colliding or being flung away. Co-formation presents another possibility, suggesting that the Earth and Moon formed together as a binary system from the primordial accretion disk surrounding the young Sun. This model implies that both bodies formed from the same material and thus share isotopic similarities. Each theory contributes a unique perspective, allowing for a broader understanding of the origins of this celestial companion. Consensus within the scientific community gradually shifted towards the giant impact theory. As evidence accumulated, this scenario posits that a Mars-sized body, often referred to as Theia, collided with the early Earth, resulting in debris that eventually coalesced into the Moon. Geological samples collected during lunar missions revealed isotopic similarities between Earth and Moon rocks, lending support to this hypothesis. Studies of lunar geology indicate a relatively dry lunar mantle, consistent with the high-energy impact scenario, which would have stripped away volatile materials. The temperature and pressure conditions during such an event could explain the Moon's unique composition, distinct from both Earth and other planetary bodies. Computer simulations have played a significant role in validating the giant impact theory. These models illustrate the dynamics of such a colossal collision, demonstrating how the debris could orbit Earth and gradually form the Moon over time. In addition, isotopic ratios of oxygen and other elements reinforced the connection between the two bodies, suggesting a shared origin. This evidence has led to a profound understanding of the Moon's genesis, aligning with the broader narrative of planetary formation in our solar system. As new techniques and technologies emerge, the exploration of lunar origins continues, unveiling deeper insights into the complexities of planetary evolution. Lunar samples obtained during the Apollo missions represent a pivotal aspect of understanding the Moon's formation and geological history. Collected between 1969 and 1972, these samples provide a direct link to the Moon's surface, offering invaluable information about its composition and age. Each sample, meticulously brought back to Earth, carries with it the history of impacts, volcanic activity, and the primordial materials that shaped this celestial body. This reveals a surface primarily composed of anorthosite, basalt, and regolith, highlighting the Moon's complex geological processes. Radiometric dating techniques applied to the lunar rocks indicate that the majority of the surface is approximately 4 billion years old, suggesting a period of intense bombardment shortly after its formation. These materials also elucidate the Moon's connection to Earth, with isotopic similarities suggesting a shared origin. This evidence supports the giant impact hypothesis, proposing that a Mars-sized body collided with the young Earth, resulting in debris that coalesced to form the Moon. Research on these samples continues to evolve, employing advanced methods such as mass spectrometry and electron microscopy. Insights gained from lunar materials not only enhance our understanding of the Moon itself, but also contribute to broader theories regarding the formation and evolution of terrestrial planets within the solar system. Radiometric dating techniques provide a critical framework for determining the age of lunar rocks. By measuring the decay of radioactive isotopes within these samples, scientists can ascertain the time that has elapsed since their formation. Isotopes such as uranium and thorium undergo predictable decay processes, allowing for precise calculations of geological timelines. The age determination of lunar rocks reveals a complex history, with samples collected during various Apollo missions, yielding ages ranging from 3 billion to nearly 4.5 billion years. These findings indicate that the Moon's surface has undergone significant geological activity, including volcanic eruptions and impact events, shaping its current landscape. Analysis of specific rock types, such as basalt and anorthosite, provides insight into the Moon's evolution. Basalts, formed from the solidification of molten lava, often reveal younger ages, while anorthosites, composed primarily of plagioclase feldspar, are typically older, suggesting an ancient crust formed during the Moon's early history. Additionally, the presence of impact craters and their associated ejecta offers further context for age determination. The distribution and morphology of these features assist in correlating rock ages with specific impacts. This understanding not only elucidates the Moon's geological past, but also aids in comparing lunar and terrestrial processes, bridging gaps in planetary formation theories. The lunar regolith serves as a vital archive of its history, capturing the remnants of billions of years of cosmic events. This fine layer of dust and fragmented rock reveals the Moon's surface composition and its interactions with solar and cosmic radiation. By analyzing the regolith, scientists glean insights into the Moon's volcanic activity. the impacts from meteorites, and the effects of solar wind, intense bombardment from celestial bodies over millions of years, has contributed to its unique characteristics. The presence of tiny glass beads formed from high-energy impacts highlights the dynamic processes that have shaped this environment. Furthermore, the regolith contains minerals such as plagioclase and olivine, providing clues about the Moon's volcanic history and its mantle's composition. Radiometric dating techniques applied to lunar samples have uncovered a timeline of geological events, revealing periods of intense activity followed by relative calm. This chronology aids in understanding not only the Moon's evolution, but also the broader context of planetary formation within the solar system. The regolith's interaction with micrometeorites leads to a continuous alteration of its surface, creating a record of changes that extend beyond mere geological phenomena. By studying these clues embedded within the regolith, researchers piece together the story of a satellite that has witnessed the unfolding of solar system history. Understanding the Moon's atmosphere reveals insights into its formation and evolution. This tenuous envelope, known as an exosphere, consists of trace gases, predominantly hydrogen, neon, and argon. These elements fail to accumulate in significant quantities due to the Moon's low gravity, allowing them to escape into space with ease. The exosphere serves as a remnant of the primordial gases present during the Moon's formation, providing a glimpse into the conditions that prevailed shortly after the colossal impact event. The volatile compounds released during this period, along with those delivered by comets and solar wind, contributed to the composition of this faint atmosphere. Gases occasionally escaping from the lunar surface interact with solar radiation, leading to various physical processes that further affect the exosphere's density and structure. This delicate balance results in a dynamic system characterized by fluctuations in gas concentration, influenced by factors such as sunlight and the Moon's position relative to Earth. These subtle interactions are crucial for understanding the impact of space weathering on the lunar surface. The absence of a significant atmosphere means that the Moon is vulnerable to the harshness of solar and cosmic radiation, shaping its environment and geological features over billions of years. Insights gained from studying this exosphere illuminate the Moon's complex history and its role within the broader context of the solar system. The evolution of lunar geology reveals a dynamic timeline, beginning with its formation approximately 4.5 billion years ago. This period marked the aftermath of a colossal impact, where a Mars-sized body collided with the early Earth, ejecting debris that coalesced into the Moon. This initial phase saw the creation of a molten surface, which gradually cooled, leading to the solidification of a basalt crust. Subsequent volcanic activity contributed to the development of vast basalt plains, known as lunar moraines. These dark expanses formed from ancient lava flows, serving as a stark contrast to the heavily cratered highlands. Over millions of years, impact cratering became the predominant geological process, shaping the surface with a multitude of craters, ranging from small pocks to massive basins. Each impact recorded a moment in time, preserving the history of celestial interactions. The absence of significant atmospheric erosion allows these features to remain remarkably well preserved. Radiometric dating techniques have revealed the age of these geological formations, allowing scientists to construct a timeline of events that reflect the Moon's tumultuous past. Present-day observations indicate that while the Moon is now relatively inactive, it continues to evolve subtly, with the potential for future volcanic activity. Understanding this evolution provides critical insights into both lunar history and the broader processes that govern planetary development. The formation of the Moon has significant implications for Earth's climate history. The collision that led to its creation not only altered the trajectory of the planet but also affected its rotational dynamics. This change in rotation has played a crucial role in stabilizing Earth's axial tilt, which in turn regulates seasonal variations and long-term climate patterns. The presence of the Moon contributes to the tidal forces experienced on Earth. These forces are vital in maintaining ocean currents and influencing atmospheric circulation. The movement of water, driven by lunar gravity, helps to moderate temperatures and create a more hospitable environment for life. Variations in Earth's axial tilt, influenced by the Moon, led to cyclical changes in climate over thousands of years. These cycles, known as Milankovitch cycles, are essential for understanding past ice ages and warmer periods. The interplay between the Moon and Earth's climate system underscores the interconnectedness of celestial objects and planetary environments. As the Moon continues to exert its influence, its effects on climate extend beyond mere temperature regulation. It shapes ecosystems and biodiversity, impacting the evolutionary trajectory of numerous species. This relationship between the Moon and Earth illustrates how celestial events can cascade through time, guiding the development of complex systems on a planetary scale. The Moon's gravitational pull plays a crucial role in stabilizing Earth's axial tilt. This relationship contributes to a more consistent climate over geological timescales. Without this satellite, the planet would experience significant fluctuations in its tilt, leading to dramatic shifts in climate and environmental conditions. Observations indicate that the current axial tilt of approximately 23.5 degrees promotes a stable climate, which in turn supports diverse ecosystems. Tidal forces, generated by the Moon's orbit, result in oceanic movements that shape coastal environments. These tides affect marine life and contribute to nutrient distribution across vast regions. As these ecosystems evolve, they foster biological diversity, further intricately linking the Moon's presence to life on Earth. The gradual slowing of Earth's rotation, primarily influenced by lunar gravity, creates longer days over millions of years. This process affects the patterns of sunlight reaching the surface, influencing photosynthetic cycles and weather systems. It also impacts the timing of seasonal changes, with cascading effects on agricultural practices and food production. In addition, the Moon serves as a reference point for navigation and timekeeping throughout history. Cultures have developed calendars and agricultural practices based on its phases, underscoring its impact on human civilization. This dynamic relationship between Earth and its Moon continues to shape both the planet and life itself in profound ways. The Moon serves as a geological laboratory, offering insights into the processes that govern planetary formation. Its surface is a rich archive, marked by ancient impact craters and basaltic plains. These features provide clues about the early history of the inner solar system, revealing a time when planetary bodies were still forming and colliding with one another. The lack of atmosphere on the Moon preserves its geological history, allowing scientists to study the composition and age of lunar rocks. Samples returned by the Apollo missions have revealed the isotopic signatures of primordial materials, shedding light on the conditions present during the formation of terrestrial planets. The age of these samples, some dating back more than 4 billion years, suggests a timeline for the evolution of the solar system. Variations in regolith composition across different lunar regions indicate diverse geological processes at play. The presence of volcanic material points to a once active interior, hinting at the moon's thermal history. Additionally, the study of these rocks has provided insights into the dynamics of magma ocean formation, a phenomenon also believed to have occurred on Earth. Understanding the moon's geological history not only illuminates its own past, but also enhances knowledge of the mechanisms that shaped the planets. Each layer of lunar regolith encapsulates a story, contributing to a broader comprehension of planetary evolution. The lunar cataclysm marks a period when the moon, along with other celestial bodies, experienced intense bombardment from asteroids and comets, occurring approximately 4 billion years ago. This era significantly shaped the surface of the moon, creating numerous craters that remain visible today. Impact events during this time were not isolated incidents. Rather, they represented a sustained barrage, altering the moon's topography and geological history. This region bears the scars of these impacts, with craters ranging in size from mere meters to hundreds of kilometers in diameter. Each indentation serves as a record of the energy released during the collisions, offering insights into the dynamics of the early solar system. The sizes and distribution of these craters provide clues to the frequency and scale of the bombardment, revealing a chaotic environment fraught with celestial debris. The geological consequences extended beyond mere surface alteration. These impacts generated significant heat, leading to melting and reformation of lunar regolith. Such processes contributed to the moon's differentiation, influencing its crust, mantle, and core. Despite the tumultuous nature of this period, it played a crucial role in the evolution of not only the moon but also other planetary bodies within the solar system. Underscoring the interconnectedness of celestial phenomena, geological diversity on the moon reveals a complex history shaped by various processes. The highlands, characterized by their rugged terrain and lighter-colored surfaces, consist of a northocite, which is predominantly composed of plagioclase feldspar. These elevated regions are ancient, dating back over 4 billion years, a testament to the early bombardment that shaped their formation. Their heavily cratered appearance serves as evidence of sustained impacts, reflecting the moon's role in the chaotic environment of the early solar system. In contrast, the Maria present a starkly different landscape, formed by ancient volcanic activity. These smooth, dark plains are rich in basalt, a volcanic rock that indicates a more recent geological history. Unlike the highlands, the Maria are younger, with ages spanning from 3 billion to around 2 billion years. Their relatively flat surfaces suggest a period of volcanic flooding, which filled pre-existing basins, creating expansive regions devoid of significant cratering. This variation in surface composition and age illustrates not only the geological processes that have shaped the moon, but also hints at its thermal evolution. The stark differences between the highlands and Maria offer insights into the moon's cooling history and tectonic activity, suggesting a dynamic past that continues to intrigue scientists studying its formation and evolution. Cultural interpretations of the moon reflect humanity's enduring fascination with its presence in the night sky. Early civilizations often ascribe divine significance to this celestial body, viewing it as a powerful symbol in their mythologies. The moon served as a harbinger of time, guiding agricultural practices and ritualistic calendars. In various cultures, its phases were imbued with meaning, from the new moon signaling new beginnings to the full moon representing culmination and fulfillment. The concept of the moon's origin has shifted dramatically, particularly with the advent of modern science. Early beliefs attributed its formation to supernatural forces or the actions of deities, As the field of astronomy progressed, these narratives evolved. The giant impact theory emerged in the late 20th century, positing that a Mars-sized body collided with the early Earth, resulting in the ejection of debris that coalesced into the Moon. This scientific explanation intertwined with cultural narratives, reshaping perceptions of the Moon as a product of cosmic events, rather than divine intervention. Art and literature throughout history have echoed this duality, depicting the Moon as both a distant orb and an integral part of human existence. Its luminous glow has inspired countless works, serving as a muse for poets, painters, and thinkers, who reflect on its significance and the mysteries of existence it embodies. The influence of lunar phases extends beyond mere inspiration, subtly shaping the rhythms of life on Earth. Historically, agriculture relied heavily on the waxing and waning of this celestial body. Farmers observed its cycles, aligning planting and harvesting with the lunar calendar. The belief in the Moon's power to affect plant growth remains prevalent in various cultures, illustrating a deep-rooted connection between cycles and nourishment. Tides, driven by its gravitational pull, profoundly impact coastal ecosystems and human activities. The predictable rise and fall of sea levels dictate fishing practices, with certain species more abundant during specific lunar phases. This reliance illustrates a long-standing relationship between humanity and the Moon's gravitational influence, fostering a symbiotic balance. Sculptural rituals and traditions often correlate with lunar cycles. Festivals, celebrations, and religious observances frequently align with full moons. Harnessing its symbolic significance, communities gather to honor the lunar phases, reflecting a collective acknowledgement of its presence in daily life. In matters of health, historical beliefs suggest variations in human behavior, and emotional states are linked to the Moon. Sleep patterns, mood fluctuations, and even the timing of certain medical procedures have been influenced by its phases, revealing an intricate connection between the cosmos and terrestrial existence. These observations underscore the enduring impact of the Moon on Earth, shaping life in profound and often understated ways. Scientific inquiries into the Moon have catalyzed numerous advancements across various disciplines. Its presence has guided humanity's understanding of celestial mechanics, influencing theories of gravitational interactions. These studies reveal the intricate relationship between the Earth and its satellite, offering insights into tidal forces that have shaped coastlines and ecosystems. Observations of lunar phases have led to the development of calendars, allowing civilizations to mark time and organize agricultural practices. The Moon's surface has served as a natural laboratory for geological processes, revealing insights into planetary formation and evolution. Robotic missions have provided data, enabling comparisons between the Moon's geology and that of other celestial bodies. From Hitcom, human curiosity propelled manned missions, marking significant milestones in explorations. These journeys expanded knowledge of space travel, resulting in technologies that have permeated everyday life on Earth. Instruments designed for lunar research have led to advancements in materials science, telecommunications, and even medical imaging. The Moon continues to inspire new generations of scientists and explorers. Current initiatives aim to establish a sustainable human presence, potentially serving as a stepping stone for further exploration of Mars and beyond. Each mission contributes to a growing repository of knowledge, underscoring the vital role the Moon plays not just in the cosmos, but in shaping the trajectory of human scientific endeavors. Current scientific inquiries continue to illuminate the Moon's enigmatic nature, revealing gaps in understanding that inspire further explorations. The precise details of its formation remain a topic of debate, with the giant impact theory serving as a prominent framework. While this hypothesis suggests that a Mars-sized body collided with the early Earth, creating debris that the Moon's surface, marked by its striking maria and rugged highlands, still holds secrets beneath its regolith. Studies have yet to fully elucidate the composition of the lunar mantle and the processes that shaped its geological history. Insights into its volcanic activity and the timing of such events remain incomplete, leaving room for speculation about its thermal evolution. Additionally, the presence of water ice at the lunar poles raises questions about its origin and stability. Understanding the distribution, quantity, and potential accessibility of these resources could significantly impact future exploration endeavors. The Moon's magnetic field, weak and fragmented, adds another layer of mystery, compelling scientists to probe deeper into its past and the role it may have played in shielding the Earth from cosmic radiation. These unresolved questions drive the ongoing pursuit of knowledge, prompting missions and studies aimed at unraveling the complexities of this celestial body. Advancements in planetary science increasingly reveal the intricate connections between lunar studies and broader celestial research. The Moon serves as a unique laboratory, offering insights into planetary formation and processes that shaped the terrestrial planets. Samples returned from lunar missions provide critical data regarding the early solar system, highlighting the shared history of the Earth and its natural satellite. Geological features, such as the vast basalt plains known as maria, tell tales of volcanic activity and tectonic movements. These formations allow scientists to examine the cooling and solidification of magma, contributing to models of planetary evolution. It becomes apparent that these lunar characteristics reflect processes that may have occurred on Earth and other rocky planets. Isotopic analyses of lunar materials reveal the similarities and differences between the Moon and Earth, enhancing understanding of their developmental pathways. Such studies illuminate the role of impacts in shaping celestial bodies, providing a framework for investigating the histories of exoplanets and asteroids. Missions target both the Moon and beyond. The wealth of information gleaned from its surface continues to enhance knowledge of planetary systems. Each discovery fosters a greater understanding of not only the Moon itself, but also the formation and evolution of celestial bodies throughout the universe. This interconnectedness underscores the value of lunar research in the broader context of planetary science. The role of space missions has been integral in advancing our understanding of the Moon's formation. Various lunar orbiters have captured detailed imagery and data, revealing surface compositions and geological features. These observations provide insight into the Moon's history, allowing scientists to piece together the events surrounding its origin. Orbital missions, such as those launched by various space agencies, have mapped the lunar surface with unprecedented precision. Their instruments measure the mineralogy and elemental composition, offering clues that support or challenge existing theories. This data informs models of impact processes, including the dynamics of the collision that likely formed the Moon. Sample return missions have further enriched this knowledge by retrieving lunar rocks and soil. These endeavors enable direct analysis in terrestrial laboratories. The examination of isotopic ratios and mineral structures offers invaluable information about the Moon's formation and its relationship with Earth. Such samples help to clarify the timeline of geological processes and the evolution of both bodies. Collaborative international efforts to study these materials continue to yield insights. Each piece of lunar regolith tells a story, revealing the Moon's complex history and, by extension, the early solar system. Through these missions, a clearer picture emerges, connecting the dots between impact theory and the ongoing evolution of celestial bodies. The Artemis program represents a renewed commitment to lunar exploration, aiming to land the next humans on the moon while fostering a sustainable presence. This initiative seeks to build a foundation for future missions to Mars, expanding human understanding of our solar system. Primary objectives include establishing a lunar base, known as the Artemis Base Camp, which will facilitate long-term research and habitation. This region of the Moon, particularly the South Pole Aitken Basin, is of significant interest due to its potential resources. Water ice deposits discovered in permanently shadowed craters could provide essential supplies for future explorers, enabling in-situ resource utilization. The scientific community anticipates that these resources will play a crucial role in sustaining human life and operations on the lunar surface. Technological advancements will accompany these explorations, with new spacecraft and rovers designed for varied terrains. Lunar Gateway, an orbiting outpost, will serve as a staging ground for missions, allowing for easier access to the Moon's surface. Research conducted in this environment will deepen insights into the Moon's geological history and its connection to Earth. These goals reflect a broader aspiration to unify global efforts in space explorations, fostering collaboration among nations while inspiring future generations. The Artemis program symbolizes a pivotal moment in humanity's journey beyond our planet, challenging the limits of exploration and discovery. This endeavor emphasizes the Moon's role as a critical stepping stone for Mars exploration. Its proximity allows for a testing ground where new technologies can be developed and refined. The lunar surface, marked by a stark and barren landscape, presents unique challenges that mirror the Martian environment. Regolith samples collected from these desolate plains provide insights into the planetary processes that shaped both celestial bodies. Establishing a sustainable presence on the Moon can facilitate the development of life support systems and in-situ resource utilization. Water ice, discovered in permanently shadowed craters, holds potential for sustaining human life and producing rocket fuel. These resources could be pivotal in extending missions to Mars, reducing the need for extensive supplies launched from Earth. The lunar environment also offers insights into radiation exposure, a significant concern for future interplanetary travel. Conducting experiments in this region aids in understanding the effects on both human and robotic explorers. Lunar bases could serve as hubs for scientific research and international collaboration, fostering a unified approach toward exploration. The Moon's gravitational pull facilitates efficient launch trajectories towards Mars, allowing spacecraft to conserve energy and resources on their journey. Such strategic advantages highlight the Moon's integral role in humanity's next leap into the cosmos. The Moon serves as an invaluable reference point in exoplanetary studies. Its geological features, shaped by billions of years of cosmic events, offer insights into planetary formation and evolution. Analyzing its surface reveals the processes that may also govern distant celestial bodies. This region is marked by craters, maria, and highlands, each narrating a chapter of our solar system's history. The presence of water ice in permanently shadowed craters suggests that similar bodies may harbor essential resources. These findings inform the search for life beyond Earth, indicating where conditions might be favorable. The Moon's thin atmosphere, or exosphere, underscores challenges faced by exoplanets with similar characteristics. The lack of substantial atmospheric protection results in surface exposure to solar and cosmic radiation. Understanding these dynamics allows scientists to develop models predicting atmospheric retention on exoplanets. The Moon also acts as a natural laboratory for testing equipment and strategies needed for exploration of other worlds. Instruments designed for lunar missions can be adapted for use on exoplanets, streamlining future endeavors. These lessons extend beyond mere observation. They shape the methodologies employed in the quest for habitable worlds. The Moon's proximity allows for frequent study, making it an essential cornerstone in the broader framework of planetary science. Insights gained from this celestial body reverberate throughout the field, guiding humanity's exploration of the cosmos. Investigating water on this celestial body opens new avenues for understanding its history and potential for future exploration. Recent missions have confirmed the presence of water ice, primarily located in permanently shadowed craters at the lunar poles. These regions offer a unique environment where temperatures plummet, allowing water to remain in solid form for eons. The implications of this discovery are profound. Water serves as a critical resource for human exploration, potentially supporting long-term habitation and fueling spacecraft. Its availability transforms the Moon into a crucial staging ground for deeper space missions, particularly those aimed at Mars. The extraction and utilization of lunar water could significantly reduce the amount of supplies required from Earth, thereby enhancing the feasibility of sustained human presence beyond our planet. Further studies reveal that the water on the lunar surface is not merely a simple resource. It interacts with the regolith, influencing the Moon's geological processes. Understanding these interactions can provide insights into both the Moon's evolution and the broader dynamics of planetary bodies in our solar system. Exploratory missions focused on these icy deposits will likely employ advanced technologies, fostering innovation in robotic and human spacecraft. As humanity prepares for the next steps in its cosmic journey, this region of the Moon stands as a pivotal point in the quest to expand our presence in space. The Moon's magnetic field reveals significant insights into its early differentiation processes. Measurements from lunar missions indicate that this field, though weak compared to Earth's inertia, suggests a once active dynamo. Evidence points to a time when the Moon's interior was partially molten, allowing for the movement of electrically conductive materials, and this region exhibits remnant magnetization in lunar rocks, hinting at a period of intense geological activity. The varied magnetic signatures across the surface imply differences in composition and thermal history. Some areas display stronger magnetization, reflecting localized phenomena that shaped its crust. The magnetic field's variation offers clues to the Moon's evolution, suggesting a complex interplay between cooling, solidification, and the cessation of any dynamo action. Analyzing these remnants provides a timeline for the Moon's formative years. The magnetic field strength fluctuated as the body cooled, indicating periods of differentiation where heavier elements sank while lighter materials rose. Such processes contributed to the development of the crust, revealing the Moon's layered structure. Understanding these dynamics not only sheds light on the Moon's history but also parallels planetary formation across the solar system. Insights gained from lunar geology inform theories about how celestial bodies evolve, making the Moon a key player in unraveling the mysteries of planetary science. Solar wind, a stream of charged particles emitted by the Sun, plays a significant role in shaping the lunar surface. This relentless barrage interacts with the Moon's regolith, the layer of loose, fragmented material covering solid bedrock, leading to various alterations. The impact of solar wind is particularly evident in the formation of space weathering features, which contribute to the Moon's distinct appearance. As these particles collide with the surface, they induce chemical reactions and physical changes. The resulting weathering process alters the composition of lunar minerals, producing nanophase iron particles, which give certain areas a darker hue. Over time, this consistent exposure creates a variety of textures, from smooth plains to rugged highlands, each telling a story of their exposure to this constant solar influence. Additionally, the lack of a substantial atmosphere allows solar wind to interact directly with the surface, leading to processes such as sputtering and the implantation of solar wind ions into lunar materials. These ions become part of the regolith, contributing to the Moon's unique mineralogy. Understanding this interaction enhances knowledge of not only the Moon's history, but also the broader processes that shape airless bodies throughout the solar system. The insights gleaned from these studies further illuminate the intricate dance between solar phenomena and celestial surfaces, enriching the field of planetary science. The contrasts in volcanic activity between Earth and its moon provide a fascinating glimpse into their geological evolution. Earth's dynamic crust is characterized by active plate tectonics, which gives rise to frequent volcanic eruptions. This constant reshaping creates a diverse range of landforms and ecosystems, driven by the heat generated from its molten core. Volcanism on this planet is not merely a geological process. It supports life and contributes to the planet's atmospheric composition. In contrast, the Moon presents a more subdued volcanic history. Once considered geologically inactive, the lunar surface is dotted with vast basalt plains known as maria, remnants of ancient volcanic activity. These formations, created by lava flows around 3 billion years ago, indicate a period of significant volcanic outgassing. The Moon's lack of a substantial atmosphere and liquid water contributes to its relatively dormant state compared to Earth. The differences in volcanic behavior reflect the distinct internal structures and thermal evolution of both bodies. Earth's lively geological processes are fueled by considerable internal heat, whereas the Moon, having long since cooled, exhibits only faint geological signs of its once fiery past. These observations not only provide insights into their individual histories, but also enhance understanding of planetary formation and evolution within our solar system. Geological activity on the Moon remains an area of significant interest for scientists. Recent research has revealed that this celestial body is not the static, inert environment once presumed. Volcanic activity, although reduced, is still evident in certain regions, particularly in the younger lunar maria. These basaltic plains, formed by ancient lava flows, showcase the Moon's dynamic past. Evidence suggests that some of these flows occurred as recently as 100 million years ago, indicating that the Moon has experienced geological processes well into its later history. The discovery of small, localized volcanic features such as pits and cracks has prompted new inquiries into the mechanisms behind this activity. Seismographic data collected from lunar landers has provided further insights. Shallow moonquakes detected at various sites indicate that the Moon is not entirely geologically dormant. Such seismic events offer clues about the internal structure and thermal state of this satellite. Research into the presence of water ice in shadowed craters has opened new avenues for understanding the Moon's surface chemistry and potential for supporting future human exploration. These findings suggest that the Moon, while often depicted as a lifeless rock, possesses a complex geological history that continues to unfold. Ongoing missions and studies will likely reveal even more about this fascinating environment. Determining the Moon's age involves careful analysis of lunar samples through radiometric dating techniques. This method relies on the decay of radioactive isotopes, providing insights into the formation and history of this celestial body. Lunar rocks collected during the Apollo missions and later robotic missions serve as crucial data points. Through these samples, scientists have identified isotopes such as uranium and thorium, which decay at known rates. By measuring the abundance of these isotopes and their decay products, researchers can calculate the ages of various rock types. The oldest rocks, dated at approximately 4,500,000,000 years, hint at the Moon's formative period shortly after the giant impact event that is hypothesized to have created it. These findings not only establish a timeline for the Moon's evolution, but also offer clues about the early solar system. The age of the lunar surface, shaped by countless impacts from meteorites, reflects a history of celestial interactions that contributed to its current state. Variations in age among different regions suggest a complex geological history, marked by volcanic activity and erosion. Continued advancements in dating techniques and instrumentation promise to refine these age estimates further, revealing the intricate details of the Moon's past and its relationship with Earth. Such knowledge enriches the understanding of planetary formation processes across the solar system. The gravitational pull of this natural satellite plays a crucial role in stabilizing Earth's axial tilt. A stable tilt fosters a relatively consistent climate, allowing for the gradual evolution of diverse biological entities. Variations in climate, influenced by the Moon, have directly impacted the development of ecosystems and the adaptability of species. Tidal forces, generated by this celestial body, shape the rhythms of life in oceans and along coastlines. They create intertidal zones that serve as critical habitats for myriad organisms. The cyclical nature of tides, essentially orchestrated by the Moon, influences reproductive cycles and feeding behaviors. Certain species synchronize their reproductive activities with lunar phases, ensuring optimal conditions for survival. These connections illustrate the intricate interplay between celestial mechanics and biological rhythms. Ecosystems on land are not immune to these influences. The Moon's presence aids in regulating nocturnal activity patterns among various terrestrial species. Behavioral adaptations, such as foraging and predator-prey dynamics, often hinge on lunar illumination, further embedding the Moon within the fabric of life on Earth. As Earth's biological history unfolds, this dynamic relationship continues to shape evolutionary pathways. The Moon stands as a silent witness to the unfolding complexity of life, its effects woven subtly into the very essence of existence on this planet. This celestial body serves as a natural observatory, providing a unique vantage point for the study of the cosmos. Its surface, marked by ancient craters and vast plains, offers an unblemished view of the universe, free from the atmospheric distortions that plague Earth-based observations. The absence of an atmosphere allows for direct measurements of cosmic phenomena, revealing insights into solar radiation and cosmic rays. With region fluctuation and cosmic rays. In this region, astronomers have utilized its landscape to host instruments that probe deep into the fabric of space. Telescopes positioned on the lunar surface can detect faint signals from distant galaxies and track the movements of asteroids and comets with unprecedented clarity. The lack of light pollution enhances the visibility of celestial bodies, facilitating studies that would otherwise remain obscured. The Moon's gravitational influence plays a pivotal role in shaping terrestrial tides, which subsequently affect Earth's climate and ecosystems. Understanding such interactions informs scientists about the dynamic relationships within the solar system. Research conducted in lunar laboratories further expands our knowledge of fundamental physics. The Moon acts as a testing ground for technologies that may one day support human exploration of more distant worlds. Each crater and ridge contributes to a deeper understanding of cosmic history, revealing the processes that sculpt not just the Moon, but the solar system as a whole. Understanding lunar eclipses offers insight into the intricate dynamics of celestial bodies. When Earth passes between the Sun and the Moon, a shadow is cast upon the lunar surface. This phenomenon occurs only during a full moon, when the three bodies align in a straight configuration. The light filtering through Earth's atmosphere creates a soft reddish hue on the Moon, a sight often referred to as a blood moon. This effect stems from Rayleigh scattering, where shorter wavelengths of light are dispersed, allowing only the longer wavelengths to reach the Moon. Such occurrences provide a unique opportunity to study the Earth's atmosphere and its composition, revealing information about pollutants, volcanic activity, and the overall climate. Lunar eclipses can be predicted with remarkable precision thanks to a comprehensive understanding of both the Moon's orbit and Earth's rotation. These predictable patterns underscore the gravitational influences at play, highlighting the delicate balance within the solar system. The cyclical nature of these events is a reminder of the interconnectedness of celestial mechanics. Observations of lunar eclipses have been recorded throughout history, serving as key markers in various cultures' calendars. This ongoing relationship between Earth and its natural satellite continues to inform contemporary astronomical research, enhancing our grasp of planetary dynamics and the universe's evolution. Oil phenomena. The orbit of the Moon has undergone significant changes since its formation, shaped by complex gravitational interactions. Initially, this natural satellite existed much closer to Earth. Over millions of years, tidal forces exerted by Earth gradually pushed it outward, resulting in the current average distance of approximately 380,000 kilometers. This process reflects the intricate balance of forces that govern celestial bodies. Long-term evolutionary models indicate that the Moon's orbit is not static. It experiences gradual variations influenced by the gravitational influence of other celestial bodies, particularly the Sun. These variations contribute to the precession of the lunar orbit, altering its shape and orientation over extensive timescales. Such dynamics provide insight into the history of both Earth and its satellite. Both Earth and its satellite. The interaction between Earth's rotation and the Moon's orbit plays a critical role in shaping tidal patterns. These tidal forces impact the planet's geological features and oceanic systems, underlining the interconnected nature of celestial mechanics. As the Moon continues its slow drift away from Earth, its gravitational influence diminishes, leading to subtle shifts in tidal behavior. Studies of these long-term changes offer a glimpse into the past, while also providing essential data for predicting future scenarios. The Moon serves as a key to understanding the complex interplay of forces that govern the evolution of planetary systems. Its gravitational influence is a fundamental force shaping Earth's geophysical processes. Tidal interactions, a direct consequence of this relationship, create rhythmic patterns in the oceans, affecting currents and marine ecosystems. These tidal forces also extend to the solid crust, resulting in a phenomenon known as solid Earth tides. This subtle movement alters the planet's surface, contributing to a dynamic, ever-changing landscape. The Moon stabilizes Earth's axial tilt, which plays a crucial role in maintaining a relatively stable climate over geological timescales. This stability allows for the gradual evolution of life, fostering diverse ecosystems that thrive in the varied environments created by seasonal changes. The axial tilt, influenced by lunar gravity, ensures that temperatures do not fluctuate drastically, promoting a balanced biosphere. Additionally, the Moon serves as a geological archive. Its surface, marked by impact craters and basaltic plains, holds vital clues about the early solar system and the processes that shaped terrestrial planets. The absence of significant atmospheric erosion on the lunar surface allows for the preservation of these ancient features, providing a timeline of events that contributed to the formation of planetary bodies. In this manner, the Moon is not merely a celestial companion. It actively participates in Earth's geophysical narrative, fostering conditions that have allowed life to flourish. The presence of unexplained phenomena on the Moon, invites curiosity and speculation. Various observations have sparked interest among researchers, such as transient lunar phenomena, which are brief flashes of light or color observed on the lunar surface. These fleeting events remain poorly understood, prompting theories ranging from gas emissions to electrostatic discharges. The Moon's surface is also home to unusual geological features, like the mysterious dark spots known as lunar swirls. These enigmatic formations reflect sunlight differently than their surroundings, suggesting unique compositional properties. This region continues to challenge scientists, leading to hypotheses regarding their formation, including magnetic field interactions and space weathering processes. In addition, the detection of water ice in permanently shadowed craters raises further questions about the Moon's history and potential for supporting future lunar exploration. This discovery has significant implications for understanding the Moon's evolution and its role in the solar system's water cycle. Intriguingly, the Moon exhibits a small but measurable seismic activity known as moonquakes, which offer insights into its internal structure. These events may be linked to tidal forces exerted by Earth, revealing a dynamic relationship between the two bodies. As investigations persist, the Moon continues to guard its secrets, balancing between the known and the mysterious. The future of lunar research promises to unveil deeper insights into its composition and history, driven by emerging technologies and methodologies. Advanced robotic missions are set to explore the Moon's surface with unprecedented precision. These autonomous systems are equipped with sophisticated sensors, allowing for detailed analysis of mineralogy, geochemistry, and topography. The deployment of high-resolution imaging and mapping tools will enable a comprehensive understanding of lunar geology. In addition to robotics, advancements in remote sensing technology will facilitate large-scale surveys of the lunar regolith. This will enhance the ability to identify potential resources, such as water ice, in permanently shadowed craters. Such findings could have significant implications for future human exploration and possible colonization efforts. New analytical techniques, including in situ analysis, will allow scientists to examine lunar samples on site, reducing the dependency on Earth-based laboratories. This approach could accelerate the pace of discovery, providing immediate results that contribute to ongoing research questions regarding the Moon's formation and evolution. Collaboration among international space agencies is fostering a shared commitment to lunar exploration. Combining expertise and resources, this collective effort may yield breakthroughs that reshape our understanding of the Moon and its relationship with Earth, illuminating the profound connections forged in the early days of the solar system. Mining prospects on the Moon present both opportunities and challenges that require careful examination. This celestial body houses an array of resources, including water ice in permanently shadowed craters and a wealth of minerals rich in helium-3, a potential fuel for future fusion reactors. These resources could support lunar habitats and provide materials for further exploration, potentially reducing reliance on Earth. The presence of this water ice, for instance, opens possibilities for sustaining human life, offering the essential ingredient for drinking water and oxygen. In addition, hydrogen and oxygen extracted from water could be converted into rocket fuel, facilitating deeper space missions. And as challenges arise in the form of the Moon's harsh environment, extreme temperature fluctuations, a lack of atmosphere, and high radiation levels create significant obstacles for mining operations. Moreover, The logistics of transporting equipment and materials from Earth require substantial investment and planning. Technological advancements will play a crucial role in overcoming these hurdles. Robotic mining systems are being developed, capable of operating autonomously in unforgiving conditions. The legal and ethical considerations surrounding lunar resource extraction also demand attention as nations and corporations navigate the complexities of planetary protection and ownership rights. Such endeavors may reshape not only lunar exploration, but also the broader framework of human activity beyond Earth. The Moon's presence evokes profound contemplation about humanity's place in the cosmos. It serves as a constant reminder of our fragility amidst the vastness of space. This celestial body has long inspired reflection, guiding philosophical inquiries into existence and purpose. It has become a symbol of aspiration and exploration, acting as a beacon for those who gaze upon it in wonder. On wonder, cultural narratives frequently intertwine with lunar imagery, embedding itself into the psyche of civilizations throughout history. These stories shape beliefs and inspire generations to reach beyond their terrestrial limitations. They often highlight a longing for connection, signaling both isolation and belonging within the universe. Concrete manifestations of this connection can be observed in the disciplines of art and science. The Moon often acts as a muse for artists, instigating creativity that transcends time and geography. Scientific endeavors, too, are fueled by its influence, pushing the boundaries of knowledge and technology. The duality of its beauty and remoteness invites both reverence and introspection. It compels humanity to confront existential questions, challenging perceptions of time, space, and the self. This celestial companion, while distant, remains an intrinsic part of the human experience, shaping not just the journey of exploration, but the very essence of what it means to be human in a vast universe. The Moon has served as a reliable reference point throughout history, guiding early navigators and explorers across uncharted waters. Its consistent presence in the night sky offered a sense of stability, allowing civilizations to develop calendars and navigation techniques. The gravitational influence of this satellite has also played a critical role in Earth's tides, contributing to the rhythms of life that early cultures relied upon for agriculture and fishing. During the age of exploration, sailors utilized the Moon to calculate their position at sea, employing celestial navigation techniques that relied on precise observations of its phases and positions. This method not only facilitated voyages across oceans, but also sparked a deeper curiosity about the heavens. The Moon's conspicuous beauty and proximity inspired early astronomers to gaze skyward, laying the foundation for modern astrophysics. In the 20th century, this interest culminated in a series of missions aimed at reaching the lunar surface. The Apollo program exemplified humanity's ambition as astronauts ventured beyond Earth's atmosphere to explore the Moon directly. These missions provided invaluable data on lunar geology and the solar system's history, contributing significantly to our understanding of cosmic evolution. The Moon thus stands as a bridge between Earth's ancient navigators and contemporary space explorers, marking an enduring legacy that transcends time. The Moon has consistently inspired fascination across various cultures, weaving into the fabric of myth and folklore. Many civilizations viewed it as a celestial deity, attributing to it powers that influence tides, agriculture, and human behavior. These stories emerged from the observation of its cyclical phases, which mirrored the rhythms of life on Earth. In ancient Sumer, it was revered as the god Nana, embodying the essence of fertility and time. Literature and art flourished under the moon's soft illumination, with poets and painters drawing inspiration from its ethereal glow. It served as a muse, catalyzing creativity and introspection, reflecting a shared human experience that transcends geographical boundaries. In many traditions, lunar phenomena were linked to the divine, prompting rituals and celebrations that sought to honor its presence. The interplay between science and mythology deepened as human understanding evolved. Early astronomers studied its surface, discovering craters and maria, revealing a more complex nature than previously imagined. This contrast between ancient beliefs and modern science illustrates how cultures adapted their understanding of the cosmos over time. The moon remains a subject of both scientific inquiry and artistic expression, embodying the intersection of knowledge and imagination that continues to captivate humanity. Influence on art and literature extends across centuries, revealing the moon as a timeless muse. Its luminous presence has inspired countless artists, shaping the aesthetics of various movements. This celestial body evokes feelings ranging from tranquility to melancholy, prompting creative expressions that resonate with the human experience. In ancient times, poets and scholars often regarded it as a divine entity, weaving its imagery into myths and allegories. The soft glow illuminated the night, setting the stage for romantic encounters and introspection. The moon's cyclic phases have been depicted in countless paintings, each artist capturing its essence through unique lenses. The Romantic period witnessed an intense fascination where it symbolized longing and unattainable beauty. Artists like Caspar David Friedrich employed its ethereal light to convey deep emotional landscapes, while poets such as John Keats and Lord Byron evoked its mystery in verses that echoed through time. Moving into the modern era, the moon continued to inspire avant-garde movements. Surrealists embraced its enigmatic qualities, exploring themes of dreams and the subconscious. Literature, too, reflects this influence, with countless narratives intertwining human stories with lunar motifs, drawing parallels between the celestial and the terrestrial. Across diverse cultural contexts, this celestial body remains an enduring figure, connecting generations through shared wonder and artistic expression. The moon's influence extends beyond mere aesthetics and mythology. Its gravitational pull plays a significant role in governing Earth's tides, a crucial mechanism influencing coastal ecosystems. This dynamic interaction promotes nutrient cycling, supporting marine life and regulating climate patterns. The orbital relationship creates a stabilizing effect on Earth's axial tilt, which in turn affects seasonal variations and long-term climate stability. In recent decades, the implications of climate change have become increasingly apparent. As sea levels rise and weather patterns shift, the moon continues to exert its gravitational influence, contributing to tidal changes that can exacerbate flooding in vulnerable coastal regions. These lunar cycles interact with the increasing frequency of extreme weather events, further complicating the relationship between natural and anthropogenic factors. The moon's presence also prompts reflection on humanity's stewardship of the planet. Its unchanging visage serves as a reminder of the delicate balance that sustains life on Earth. The observation of lunar phases, linked to agricultural practices, underscores the interconnectedness of natural systems and human activity. This celestial companion, while remote, remains a critical component in understanding Earth's climate dynamics. As researchers probe deeper into these interactions, the Moon's role as a natural satellite continues to ripple through both scientific inquiry and environmental awareness, reinforcing the need for responsible stewardship of Earth's finite resources. The influence of the Moon extends beyond the realms of science, permeating popular media and culture. Its visage adorns the canvas of countless artistic expressions, from literature to film, often symbolizing mystery and allure. This celestial body has sparked the human imagination, inspiring narratives that explore the unknown. In cinematic portrayals, it serves as both a backdrop and a catalyst for adventure, representing the ultimate frontier for exploration. In literature, the Moon's presence evokes a sense of wonder, often embodying themes of love, longing, and the passage of time. Poets and authors have long drawn inspiration from its phases, weaving intricate connections between human emotion and lunar cycles. These representations often reflect societal values, fears, and aspirations, revealing how deeply intertwined humanity is with this orbiting body. The Moon has also become a focal point in discussions surrounding space exploration, fueling public interest in scientific endeavors. Documentaries and educational programs highlight advancements in lunar research, fostering a greater understanding of its geological and astronomical significance. This fascination nurtures a collective curiosity, encouraging a new generation to explore the cosmos and confront the challenges of space travel. Through its multifaceted representations, the Moon continues to play a pivotal role in shaping cultural narratives and advancing scientific discourse, bridging the gap between humanity and the universe. Scientific achievements related to the Moon have fundamentally altered humanity's understanding of celestial mechanics and planetary formation. The Apollo missions, a monumental endeavor, revealed the Moon's geological history through the analysis of lunar rocks, providing evidence supporting the giant impact theory. This theory posits that a Mars-sized body collided with the early Earth, resulting in debris that coalesced to form the Moon. The isotopic similarities between terrestrial and lunar samples reinforce this hypothesis, illustrating a shared origin. Continued exploration of this region holds promise for future aspirations in space science and technology. Plans for sustained lunar habitation aim to establish a foothold for deeper space exploration. The Artemis program is a contemporary initiative designed to return humans to the Moon, focusing on sustainable lunar exploration and the establishment of a lunar base. Such endeavors serve as a precursor to human missions to Mars, emphasizing the Moon's strategic importance as a testing ground for life support systems and resource utilization. In the context of astrophysics, the Moon remains a scientific laboratory, offering insights into the solar system's history and evolution. The study of its surface and subsurface will deepen our understanding of planetary processes, fostering new technologies and methodologies that could be applied both on the Moon and beyond. The legacy of this celestial body continues to inspire a quest for knowledge in the vast cosmos. It serves as a reminder of the intricate processes that have shaped not only its surface, but the very fabric of our solar system. The giant impact hypothesis posits that a Mars-sized body, often referred to as Theia, collided with the early Earth approximately 4.5 billion years ago. This cataclysmic event resulted in debris that coalesced to form the Moon. Observations of lunar rock samples, collected during various missions, reveal insights into the Moon's composition. Isotopic similarities between Earth and these samples suggest a shared origin, reinforcing the theory of a violent inception. This region, characterized by its ancient craters and basaltic plains, provides a timeline of impact events that have shaped both the Moon and its home planet over aeons. Research into the Moon's formation continues to evolve, incorporating data from lunar missions and advanced simulations. It highlights the dynamic history of celestial interactions and their impact on planetary development. The Moon, in its silent vigil, holds evidence of these cosmic events, encapsulating a narrative of formation and evolution that transcends mere geological interest. Scientific interest in the Moon continues to inspire future exploration, as it offers a unique vantage point for understanding not only its own history, but also the broader dynamics of the solar system. Upcoming missions aim to establish a sustained human presence on its surface, expanding our knowledge of lunar resources and their potential applications. These endeavors emphasize the importance of utilizing in situ resources, such as water ice, which may exist in permanently shadowed craters. This resource could support life and fuel future journeys deeper into space. Automated landers and rovers will play a crucial role in this exploration, gathering data on the lunar regolith and searching for signs of past volcanic activity. The analysis of these materials may reveal insights into the Moon's formation and the conditions present during its early years. The establishment of lunar bases is envisioned as a stepping stone for missions to Mars and beyond. These outposts would serve as hubs for scientific research, testing new technologies, and facilitating international collaboration in space exploration. As lunar exploration advances, the Moon will transform into an essential focal point for humanity's endeavors in the cosmos. Each mission adds to the growing legacy of this celestial body, inviting a deeper understanding of our place within the universe's vast expanse.